Welcome to the session Calculus of Variations, Sufficient Conditions for an Extremum. A family of curves y is equal to y of xc is said to form a proper field in a given domain D of the xy plane if through any point of D there passes one and only one curve of the family. For example, inside the circle x square plus y square is equal to 1, the family of curves y is equal to c into e raised to x, c is an arbitrary constant, forms a proper field since through any point of the above circle there passes one and only one curve of the family. See figure 1. The curves of the family of parabolas y is equal to x plus c whole square inside x square plus y square is equal to 1, however, do not constitute a proper field because different curves of the family intersect inside the circle. See figure 2. If on the other hand, all the curves of the family y is equal to y of x comma c pass through a single point x0, y0, then they are said to constitute a central field over a domain D if these curves cover D without self-intersection and the point x0, y0 lies outside D. The point x0, y0 is called the center of the pencil of curves. For instance, the family of curves y is equal to cx forms a central field in the domain x greater than 0. If a field is formed by a family of extremals, then this is called a field of extremals. Let y is equal to y of x be an extremal of the variational problem concerning the extremum of I y of x is equal to integral from x1 to x2 f of x comma y dash dx, let it be equation number 1, and let the boundary points a x1 y1 and b x2 y2 be fixed. We say that the extremal y is equal to y of x is embedded in an extremal field if a family of extremals y is equal to y of x comma c can be found such that this family forms a field with the curve y is equal to y of x as a member of this field for some value of c equal to c0, say, and the extremal does not lie on the boundary of the domain D in which y is equal to y of x comma c forms a field. Similarly, if a pencil of extremals emanating from the point a x1 y1 forms a central field including the extremal y is equal to y of x, then this curve AB is said to be embedded in a central field of extremals. In this case, the parameter of the family of curves forming the field can be taken as the slope of the tangent line to the curve at A. Jacobi condition. Consider the one-parameter family of plane curves phi of x comma y comma c equal to 0. The c discriminant of this family is the locus of the points defined by phi of x comma y comma c equal to 0, dou phi by dou c is equal to 0. In general, the c discriminant includes the envelope of the above family of curves, the locus of nodal points and the locus of cusps. If we have a pencil of curves with center at a x1 y1, then a belongs to the c discriminant. Consider a pencil of extremals y is equal to y of x comma c passing through a x1 y1 such that its c discriminant is the curve nu of x comma y equal to 0. Clearly, the envelope of this pencil of curves belongs to nu of x comma y equal to 0. The point A1 where the extremal given by y is equal to y of x touches gamma is called the conjugate point of A. From figure 5, it is clear that if the point b x2 y2 lies between A and A1, then the extremals of the pencil close to AB do not intersect. Thus, the extremals close to AB form a central field which includes the arc AB. On the other hand, for the extremal AB1, the curves of pencil close to AB1 intersect. Thus, in this case, the extremal AB1 cannot be embedded in a central field. We may sum up the above discussion as follows. In order to able to embed an arc AB of the extremal in a central field of extremals, it is sufficient that the conjugate point of A does not lie on the arc. This is known as the Jacobi condition. This condition can be mathematically stated as follows. Let y equal to y of x comma c be the equation of a pencil of extremals with the center at A such that the parameter c, for definiteness, can be regarded as the slope y dash of the extremals of pencil at A. The c discriminant of the pencil is given by y is equal to y of x comma c, dou y by dou c is equal to 0. Along every fixed curve of the family, dou y of xc divided by dou c is a function of x only. Denote dou y of x comma c divided by dou c by u, where c is a fixed. Since y equal to y of x comma c is a solution of Euler equation for the extremum of I y of x in equation 1, we have f y of x comma y of x comma c comma y x dash of x comma c minus d by dx of f y dash of x comma y of x comma c comma y x dash of x comma c is identically equal to 0. Differentiating this identity with respect to c, we get f y y minus d by dx of f y y dash into u minus d by dx of f y dash u dash is equal to 0. Let it be equation number 2. This second order equation in u is known as the Jacobi equation. Here f y y of x comma y dash, f y y dash and f y dash are known functions of x, since the second argument y is a solution of Euler's equation with c equal to c naught given for the extremal AB. If the solution dou y by dou c, which vanishes at a x1 y1, since the center of the pencil belongs to the c discriminant curve, also vanishes at some point of the interval x1 less than x less than x2, then the point conjugate to a defined by y is equal to y of x comma c naught and dou y by dou c at c equal to c naught equal to 0 lies on the arc AB of the extremal with b at the point x2 y2. But if there exists a solution of equation 2 which vanishes for x is equal to x1 and does not further vanish at any point in x1 less than or equal to x less than or equal to x2, then clearly there are no points conjugate to A lying on the arc AB. Hence the Jacobi condition is satisfied and the arc AB of the extremal can be embedded in a central field of extremals with center at A. Example 1. Is the Jacobi condition fulfilled for the extremal of the functional I y of x is equal to integral from x1 to x2 f of x comma y dash dx, passing through a0 0 and b a0. Solution. Clearly, in this case, the Jacobi equation 2 reduces to u double dash minus u is equal to 0, whose solution is u equal to c1 sin hx plus c2 cos hx. Using u of 0 is equal to 0, we find c2 equal to 0, so that u is equal to c sin hx. Evidently, the curves of the pencil u equal to c1 sin hx intersect the x-axis only at x is equal to 0. Thus, we conclude that the Jacobi condition is satisfied for any value of a. Weierstrass function. Consider the extremum of the functional I y of x is equal to integral from x1 to x2 f of x comma y dash dx, where y of x1 is equal to y1, y of x2 is equal to y2. Let it be equation number 3. Further, suppose that the extremal c through a x1 y1 and b x2 y2 satisfies the Jacobi condition so that c can be embedded in a central field whose slope is p of x comma y. Of course, an extremal can be considered as embedded in a proper field as well. We determine the sign of the increment delta I of the functional I while passing from the extremal c of a neighboring admissible curve c bar. Consider the functional integral over c bar f of x comma y p plus dy by dx minus p into fp of x comma y p dx. Let it be equation number 4. This obviously reduces to integral along c f of x comma y dash dx on the extremal c, where dy by dx is equal to p. Further, the functional 4 can be written as integral along c bar f of x comma y p minus p into fp of x comma y p dx plus fp of x comma y p dy. Let it be equation number 5. which is the integral of an exact differential. In fact, the differential of the function I bar of x comma y, into which the functional I y of x is transformed on the extremals of the field, has the form d I bar is equal to f of x comma y dash minus y dash into f y dash of x comma y dash dx plus f y dash dy, which differs from the integrand in equation 5 with y dash replaced by p, the slope of the tangent line to the extremals. Now, since the integrand in 5 is an exact differential, the integral is independent of the path of integration and is known as Hilbert's independence integral. Thus, we have integral along c bar f of x comma y p plus y dash minus p into fp of x comma y p dx is equal to integral along c f of x comma y dash dx, let it be equation number 6, for any choice of the curve c bar. Hence, by using equation 5, the increment delta I is equal to integral along c bar f of x comma y dash dx minus integral along c f of x comma y dash dx can be written as delta I is equal to integral along c bar f of x comma y dash minus f of x comma y p minus y dash minus p into fp of x comma y p dx, which is equal to integral from x1 to x2 e of x comma y p y dash dx, let it be equation number 7, where e of x comma y p y dash is equal to f of x comma y dash minus f of x comma y p minus y dash minus p into fp of x comma y p, let it be equation number 8, and e of x comma y p y dash is known as the Weierstrass function. It is now clear from equation 7 that a sufficient condition for I to attain a minimum on the extremal c is E greater than or equal to 0, since it implies delta I greater than or equal to 0. Similarly, a sufficient condition for a maximum is E less than or equal to 0, since delta I is less than or equal to 0. Further, a sufficient condition for a weak minimum is that E is greater than or equal to 0 is satisfied for values of x, y close to the values of x, y on the extremal, and for values of y dash close to p of x comma y on the same extremal. But the sufficient condition for a strong minimum is that E is greater than or equal to 0 is satisfied for all values of x, y close to the corresponding values on the extremal with values of y arbitrary, so that y dash need not be close to p of x comma y on the extremal. We may thus summarize our results on sufficient conditions for an extremum of a functional given by equation 3 as follows. A weak extremum. First one, the curve C is an extremal satisfying the boundary conditions in equation 3. Second one, the extremal C must be embeddable in a field of extremals. Alternatively, the Jacobi condition must be satisfied. 3. The Weierstrass function E does not change sign at a point x comma y close to the curve C and for values of y dash close to p of x comma y on the extremal. Clearly, E is greater than or equal to 0 for a minimum and E is less than or equal to 0 for a maximum. B. Strong extremum. First one, the curve C is an extremal satisfying the boundary conditions in equation 3. Second one, it should be possible to embed the extremal in a field of extremals or Jacobi condition is fulfilled. Third one, the function E does not change sign at any point xy close to the curve C and for arbitrarily values of y dash. For a minimum, E is greater than or equal to 0 and for a maximum, E is less than or equal to 0. A link with elementary convexity. It is interesting to note that the significance of the Weierstrass condition E is greater than or equal to 0 or E is less than or equal to 0 described above can be understood in geometrical terms. If we regard f of x comma y dash for fixed xy as a function f of zeta with y dash is equal to zeta, then the condition E is greater than or equal to 0 with E given by equation 8 implies that f of zeta is greater than or equal to L of zeta, where L of zeta is the linear function that agrees with f at zeta equal to p and whose graph touches that of f at this point. This statement merely corresponds to one of the several definitions of convexity and so-called arc above tangent. We say that the function f of theta is convex at theta is equal to p if a linear function L of theta exits such that L of theta is less than or equal to f of theta for all E with equality at theta equal to p. If f is differentiating, then L is necessarily tangent at this point. See figure 7. What is interesting here is that this definition of convexity is directly linked with the Weierstrass condition E is greater than or equal to 0. We can simply say that E is greater than or equal to 0 implies that f is convex in dy by dx at dy by dx is equal to p. As a matter of fact, convexity and concavity of certain functionals are closely linked to the existence of maxima and minima of functionals. Example 2. Investigate for an extremum of the functional I y of x is equal to integral from 0 to 1 x plus 2y plus 1 by 2 y dash square dx, where y of 0 is equal to 0 and y of 1 is equal to 0. Solution. The Euler equation for this functional is y double dash is equal to 2, whose solution satisfying the boundary conditions is y is equal to x square minus x. Now in this case, the Jacobi equation is u double dash is equal to 0. Its solution satisfying u of 0 equal to 0 is u of x is equal to c into x. Since u of x is equal to c into x does not vanish for c not equal to 0 anywhere in the closed interval 0, 1 except x is equal to 0, it follows that the Jacobi condition is fulfilled and the extremal y is equal to x square minus x can be embedded in the central field of extremals given by y is equal to x square plus c1x with center at the origin 0, 0. Now the Weierstrass function is e of x comma y comma p comma y dash is equal to 1 by 2 into y dash minus p whole square. Clearly E is greater than or equal to 0 for arbitrary y dash. Thus a strong minimum equal to I of x square minus x minus 1 by 3 is attained on the extremal y is equal to x square minus x. Legendre condition. In some variational problems, testing the sign of E may pose some difficulties. That is why an alternative condition which is readily verifiable is desirable. We assume that the function f of x comma y dash is thrice differentiable with respect to y dash. Then by Taylor's formula we have f of x comma y dash is equal to f of x comma y p plus y dash minus p into fp of x comma y p plus half of y dash minus p whole square into f y dash of x comma y q. Let it be equation number 9, where q lies between y dash and p. Thus from equation 8, e of x comma y y dash is equal to half of y dash minus p whole square into f y dash of x comma y q. Let it be equation number 10. Hence the sign of E is the same as that of f y dash of x comma y q. For a weak extremum, therefore, f y dash of x comma y q must retain its sign for values of x and y close to the points of extremal under consideration and for values of q close to p of x comma y. Now, if f y dash of x comma y dash not equal to 0 at all points of the extremal C, then by virtue of continuity, f y dash of x comma y dash maintains its sign at points close to the curve C and for values of y dash close to values of y dash on C. Thus, for testing for a weak minimum, the condition is greater than or equal to 0 may be replaced by f y dash is greater than 0 on the extremal C, and for testing for a weak maximum, the condition is less than or equal to 0 may be replaced by f y dash is less than 0 on C. This is known as the Legendre condition. On the other hand, if f y dash of x comma y q is greater than or equal to 0 at points x y close to points of C and for arbitrary values of q, then equation 10 implies that a strong minimum is attained on C. Of course, here it is assumed that the formula 9 holds good for any y dash. The above results can be readily extended to functional of the form I of y on x, y2 of x, etc., yn of x is equal to integral from x1 to x2 f of x, y1, y2, etc., yn, y1 dash, etc., yn dash dx. In this case, the Weierstrass function is E is equal to f of x, y1, y2, etc., yn, y1 dash, etc., yn dash minus f of x, y1, y2, etc., yn, p1, p2, etc., pn minus summation I varies from 1 to n, yi dash minus pi into fp of x, y1, y2, etc., yn, p1, p2, etc., pn, where pi are the slope functions of the field. The Legendre condition in this case becomes f y1 dash greater than or equal to 0, determinant of f y1 dash f y1 dash y2 dash f y2 dash y1 dash f y2 dash y2 dash is greater than or equal to 0, etc., determinant of f y1 dash f y1 dash y2 dash, etc., f y1 dash yn dash f y2 dash y1 dash f y2 dash y2 dash, etc., f y2 dash yn dash, etc., f yn dash y1 dash f yn dash y2 dash, etc., f yn dash is greater than or equal to 0. Example 3. Test for an extremum the functional I of y is equal to integral from 0 to 2 e raised to y dash plus 3 dx, where y of 0 equal to 0, y of 2 is equal to 1. Solution. The extremals are clearly the straight lines y equal to c1x plus c2. The extremal satisfying the boundary conditions is y equal to x by 2. It can certainly be embedded in the central field of extremals y equal to c into x. Here f y dash is equal to e raised to y dash, which is greater than 0 for all y dash. Thus a strong minimum is attained on y is equal to x by 2. Second variation. It is instructive to note that the sufficient conditions for a weak extremum may be derived by a technique based on the sign of the second variation of the functional 3. Delta I is equal to integral from x1 to x2 f of x, y plus delta y dash plus delta y dash minus f of x, y dash dx, which is equal to integral from x1 to x2 fy into delta y plus fy into delta y dash dx plus half of integral from x1 to x2 fyy into delta y square plus 2 into fyy delta y into delta y dash plus fy dash into delta y dash square dx plus r. Let it be equation number 11, where r is of order higher than second in delta y and delta y dash. On the extremal, the first variation represented by the first term on the right of 11 vanishes. Hence, for investigating weak extremum for which both delta y and delta y dash are small, equation 11 shows that the sign of delta I coincides with that of delta square I, the second variation being given by delta square I is equal to integral from x1 to x2 fyy into delta y square plus 2 into fyy into delta y dash plus fy dash into delta y dash square dx. Let it be equation number 12. Consider the integral involving the differentiable function g of x. Integral from x1 to x2 g dash of x into delta y square plus 2 into g of x into delta y dash dx. Let it be equation number 13, which vanishes by virtue of the boundary conditions 3, because the integral is integral from x1 to x2 d of g of x into delta y square is equal to g of x into delta y square between x1 and x2 is equal to 0. Adding equation 13 to the second variation above, we get del square I is equal to integral from x1 to x2 fyy plus g dash into delta y square plus 2 into fyy delta y into delta y dash plus fy dash into delta y dash square dx. Let it be equation number 14. The integrand is a perfect square if fy dash into fyy plus g dash minus fyy dash plus g whole square equal to 0. Let it be equation number 15. For such a choice of g, equation 14 gives delta square I is equal to integral from x1 to x2 fy dash into delta y dash plus fy dash plus g divided by fy dash into delta y the whole square dx. Thus the sign of del square I is the same as that of fy dash y dash. But such a transformation is possible provided equation 15 admits of a differentiable solution g of x. Substituting g of x is equal to minus fy dash minus fy dash y dash into u dash by u in equation 15 leads to fyy minus d by dx of fyy dash into u minus d by dx of fy dash y dash into u dash is equal to 0, which is the Jacobi equation derived earlier. If a solution u of this equation exists that does not vanish in the closed interval x1, x2, that is, if the Jacobi condition is satisfied, then clearly there exists a differential function g of x satisfying equation 15. Thus, fulfillment of both Legendre and Jacobi conditions ensures that the sign of a second variation delta square I does not change. Hence, they constitute sufficient conditions for a weak minimum if y dash is greater than 0 or weak maximum if y dash is less than 0. Another sufficient condition for the minimum of functional specified on a normed space is as follows. For a functional I y of x defined on a normed space with usual norm, to have a minimum at a stationary point y equal to y naught of x, it is sufficient that the second variation delta square I of y naught comma delta y dash defined by equation 12 satisfies the condition delta square into I of y naught comma delta y dash is greater than or equal to k into norm of delta y square, where k is a positive constant. Let me summarize this session. In this session, we have discussed the sufficient conditions for an extremum of functionals. We have discussed Jacobi condition, Weierstrass function and Legendre condition. Jacobi condition. In order to able to embed an arc AB of the extremal in a central field of extremals, it is sufficient that the conjugate point of A does not lie on the arc. For an extremum of a functional, I y of x is equal to integral from x1 to x2 f of x comma y dash dx, where y of x1 equal to y1, y of x2 equal to y2, we have the following results on sufficient conditions. First one, the curve C is an extremal satisfying the given boundary conditions. Second one, the extremal C must be embeddable in a field of extremals. Alternatively, the Jacobi condition must be satisfied. Third one, the Weierstrass function E does not change sign at a point xy close to the curve C and for values of y dash close to p of x comma y on the extremal. Clearly, E is greater than or equal to 0 for a minimum and E is less than or equal to 0 for a maximum. These results are held for both weak extremum and strong extremum. We have seen that the definition of convexity is directly linked with the Weierstrass condition E is greater than or equal to 0. Also, we discussed the second variation of the functional. Now, you have some questions, try to answer. First one, find the minimum of the functional I of y is equal to integral from 0 to 1 half of y dash square plus y into y dash plus y dx, if the values at the ends of the interval are not given. Second one, explains Weierstrass function and find out the sufficient conditions for an extremum of the functional I of y of x is equal to integral from x1 to x2 f of x comma y dash dx, where y of x1 equal to y1, y of x2 equal to y2. Third one, what is Jacobi's condition for an extremum? Fourth one, explain Legendre condition. For your reference, you may go through the following books. First one, Differential Equations and Calculus of Variations by L. Elsgolds, Mir Publishers, Moscow, 1973. Second one, Calculus of Variations with Applications by A.S. Gupta, Prentice Hall, New Delhi, 2009. Third one, Complementary Variational Principles by A.M. Arthurs, Clarendon Press, Oxford, 1970. Fourth one, Differential Equations and Their Applications by Sever, Prentice Hall, New Delhi, 2006. Hope that you have followed this session. We will meet again with another topic. Thank you.